Hello, everyone, and welcome to the last content discussion of CS61B for spring 2021. Congrats on making it through most of the semester. We're almost there, so keep pushing through. Today, we're going to cover some more sorting, and first, we have some announcements. The ones that are relevant by the time this video is released on Wednesday. Project 3 Phase 2 is due Tuesday, April 27th. There are no slip days whatsoever for that. And homework 3, which is some more conceptual review, is due on Monday, May 3rd. And again, there are no slip days for that because we'll release the solutions afterwards so you can study with them. With that all being said, we can jump into the content review. So first, I want to talk a little bit about our vocabulary when discussing radices. I don't know what the plural is, but a radix, singular, can be thought of as the alphabet or set of digits to choose from in some system. Properly, it is defined as the base of a numbering system. But we can use this term a little more vaguely when we're talking about radix sorts. And so here we say, for example, the English alphabet is a radix. In the context of radix sorts and stuff, we can consider it a radix, even though it's not the base of a numbering system. And the radix size of the English alphabet is 26 for A through Z. And the radix size of Arabic numerals is 10, going 0 through 9. And so both the alphabet and numbers and other things like maybe, let's say, a card suit, right? Where you have diamonds, I think this one's clubs, spades, and hearts, right? That's also a radix with a radix size of 4. So there are plenty of ways that we can define a radix, or I guess like examples of radixes, whatever the plural is. And when we have this well-defined radix and we want to sort, we want to sort words, which consist of characters within these radixes, we can use a radix sort. So radix sorts work by using counting sorts to sort the list one digit at a time. And so there are two main types of radix sorts we look at: least significant digit and most significant digit. So least significant digit is an example of a radix sort. We call it LSD. It's super crazy, super cool. And it works by sorting digits from lowest digit to largest digit. So the idea would be that if, let's say, we had a bunch of numbers and they were like, I don't know, 4, 0, 3, 2, 1, we would sort this list, let's say, by looking at the lowest digits first, and then looking at the next digits, and so on and so forth. And we are going to sort basically one digit at a time. We'll see an example of how this actually works on the worksheet, so I won't run through how it looks exactly. But the main idea is that you're sorting these words from lowest digit to largest digit. The runtime of LSD radix sort is going to be W times n plus r, where W is the size of your largest word, N is the number of words, and R is the radix size. And so here, if I had like, let's say I was doing it with strings and I had cat, dog, can, and this was my example, W would be 3 because all of my words are 3 letters. N is also 3 because I have 3 items in the list. And R is 26 because I'm using the English alphabet. So that's LSD radix sort. MSD radix sort is super similar. It does the pretty much same thing as LSD, except we're going from largest digit to smallest digit. And we'll see an example of this on the worksheet again, so I'm not going to run over exactly how it works. But no matter what words we have, we just know we're going to be sorting here and then moving over to smaller digits as we go. And so here the runtime is big O of W times N plus R, where again, we have the same definitions of W, N, and R as an LSD radix sort. And you might notice that the runtime of LSD radix sort we say is theta of W times N plus R, whereas for MSD, that's actually a big O bound. And so when we go through the worksheet, you'll see exactly how this matters or why this is. But the basic idea is that when you're looking at the most significant digit first, you might not necessarily have to look at the whole word. Because let's say our list looked something like this, right? And so we're sorting these strings. And so here, again, we have W, we'll go with 5 because that's the size of the largest word. We have 3 words in our list and our radix size is 26. But the thing is, since we look at the most significant digit first, we're going to compare A, C, and D. And now because of this, we realize no matter what, in alphabetical order, it's going to go apple, cat, dog. This item, then this item, then this item. The lower order digits don't matter because something that starts with the letter A is always going to come first in alphabetical order over something that starts with the letter C. It doesn't matter if the rest of the lower order digits here were A, Z, 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 like the last thing it could possibly be. And the rest of the letters here were the highest or like smallest value they could possibly be, right? Because the fact that this one starts with C and this one starts with A means A will always come before this second item in alphabetical order. And so we can just look at these first letters and then end. We don't have to look at the lower order digits because they're not going to overpower this higher order digit, or the higher order digit matters more. And so because of this, in the best case scenario, MSD radix sort can actually run just in terms of the number of items and the radix size, because we're just going to be looking at every single item and the values that are here are proportional to the radix size. And so we don't have to go look through every single letter, which means the length of the word doesn't matter. We're only looking at the first digit, so the length, or W, does not matter. And so in the best case, we actually have a runtime of O of n plus R, or theta n plus R, in the best case. So because of this, if the best case is theta n plus R, and the worst case is theta W n plus R, then we can say a big O bound, or in other words, an upper bound on how bad or slow this algorithm could possibly be is W n plus R. And so because that is an upper bound, we can say that the runtime of MSD radix sort overall is in big O of W times n plus R. Finally, we're going to talk really quickly about Quicksort. We went over it briefly last week, but now we want to talk about the details of different partitioning schemes. So a simple partitioning scheme for Quicksort is basically doing 3 scans of the list. And so if you recall, the basic idea with pivoting or partitioning, right, is that if you had a list that looked like, let's do like 3, 5, 2, 4, 1. Let's say this was your list. The idea is that you pick a pivot and you somehow want to put all the elements that are less than the pivot on one subarray, then the pivot, and then everything that's greater than the pivot, right? That's the idea behind partitioning on a high level. And so one specific way of doing this is 3 scan partitioning, where you do 3 scans of the list, first putting in all elements less than the pivot, then putting in all elements equal to the pivot, and finally elements that are greater. This technique is not in place because we have to copy everything over to the secondary array. And so again, we're going to go over an example of this in the worksheet, so I won't walk through the details right now. 3-way partitioning is simple. Basically, the idea is that you're just looking over the whole thing, but there's actually a faster and much more efficient way to do this, and it's in place, which means it's also better for memory. The idea is that we use a pair of pointers that start at the left and right edges of the array and move towards each other. The left pointer likes things that are less than the pivot, and the right likes things that are greater than the pivot. And so we can imagine that maybe our pivot here is 3, and the left pointer is starting at the first thing that's not the pivot, and the right pointer is starting at the very right, right? And so this pointer likes things that are less than the pivot. And the other thing likes things that are greater. The right pointer likes things that are greater. So this is how the algorithm starts. And the idea is that both pointers are going to walk until they see something they don't like. And we recall left pointer doesn't like things that are equal to or greater than the pivot. And right pointer doesn't like things that are equal to or less than the pivot. So let's say you're walking down and left pointer goes, hey, I see this 5 and I do not like this. 5 is greater than our pivot right now, which is 3, right? And so left pointer pauses and says, I'm sitting right here until you have something to trade with me, right pointer, because I do not like this 5. I don't want to move on until I see something that's better. So left pointer sits there. And then right pointer goes, wait, this is perfect. I also don't like what I'm pointing at because 1 is less than the pivot and I only like things greater than the pivot. And so left and right go, okay, we both don't like what we have right now. Let's trade. And so these swap. And now left and right go, okay, I'm satisfied. I can move on. And so left pointer moves up and right pointer moves down. They're walking towards each other, right? And so at this current step, left pointer goes, oh, I'm good with this. Like 2 is less than our pivot. I can move on. And right pointer goes, yeah, I'm good with this too, because 4 is greater. At this point now, they have crossed. And so I want you to understand that the basic idea of what just happened is that we've got all the things that are less than the pivot on the left and all the things that are greater than the pivot on the right. And this is because we were swapping whenever something seemed wrong. And so now that the pointers have crossed, it means we've sort of met in the middle, right? We did all the things that were less, all the things that are greater, and we're done. And so because right and left have swapped, we know we're pretty much done. And the last step is to just move the pivot to the current location of the right pointer. And so we just swap 2 and 3. I guess the pointer doesn't really matter because we finished this one iteration of Quicksort. And so you can see that at this iteration, we have successfully partitioned our array around our pivot 3. And all the things that are less than 3 are to the left, and all the things greater than 3 are to the right. And the pivot and any equal items, if there were any, are in the middle. Or in this example, the pivot and equal items are in the middle. In practice, equal items might not necessarily be in the middle. And so by running for partitioning, we have completed all these steps in our little example, and we see that we've done our task, and now we can recursively call Quicksort again on these subarrays, right? And we'll do that for the left and right halves every time. And so the high level idea behind Hoare partitioning is that basically you want things less than on the left and things greater than on the right. So these pointers walk towards each other, continually checking to make sure items on their side meet the criteria. And if they don't, they're going to sit there and wait until the other pointer has something to trade. And so that is the idea behind Hoare partitioning, and it's how one efficient way that we can do in-place partitioning for Quicksort. With all that, we are done with the content review and ready to move on to the worksheet.